Thanks, Peter. Thanks for having me here. Yeah, so what I'll talk about today is about explainable AI and my perspective on it. So I'm a research scientist at IBM TJ Watson Research. And over the last, say, around 5 years or so, I've been working on this topic of explainable AI. And before that, I mean, I did stuff like across various industries that I worked on. So taking some from that experience and like what clients and other folks want, that kind of motivated me to sort of look into this sub area of AI. So what I'll do in the talk is basically give you sort of a very brief intro about explainable AI, and then share my perspective on it being kind of a two-stage approach. And then also sort of briefly go over the toolkit that we open sourced a few years back, just to show you like what all it has, and like so that if it's of use in your sort of daily work. So as we all know, AI now is being used in many things, from credit to employment to admissions to prison sentencing and so on and so forth. And so no longer it's sufficient to have like a model that does really well just on your test set. So you would say something like 99% accuracy. There are all these sort of social questions that have come up, such as, is the model fair? Is it easy to understand? Can it be tampered with? And is it accountable, and so on and so forth. And so one of the ways of making AI sort of be more transparent and sort of answering some of the questions that I mentioned before in the previous slide is through explainability. And there has been a lot of media attention given to explainable AI, where given essentially the black box nature of many of these approaches, there's a huge desire to try to understand reasons behind their decisions. And I mean, this is obvious, but one of the reasons this has happened is because over the last 10 years or so, rather than people using, say, things on the left, right, like decision trees where it's obvious how the decision was made, people are using things more or less on the right, where you have these very complicated sort of neural architectures, which are definitely not directly sort of interpretable. Also in Europe, as many of you might be aware, a few years back, the GDPR, or the General Data Protection Regulation, was passed, which asks for meaningful information about decisions that are made on behalf of humans. So any sort of human has a right to sort of challenge certain things that are recommended on his behalf to corporations and so on and so forth, asking as to why that was done. So besides trust, are there sort of other applications of explainable AI? So one application is actually simplification. So some years back, there was this huge neural network which was trained to essentially detect malware from regular code. And it had a very high accuracy. And so people sort of assumed that it was doing something really fancy, looking at a lot of really intricate aspects of the code to figure this out. But then there was a group which sort of tried to understand as to why really this was happening. And they found out that actually 99% of the accuracy of the network was just checking the code for comments. Because of course, presumably, if you have malware, the person is not going to comment the code. So just searching for comments essentially was sufficient. So in this case, you obviously don't want a classifier which just does that. But in case you were happy with it, you can basically replace the whole model with just a single rule, which just checks for comments, and you can essentially replicate the performance. So, so this is one benefit in terms of sort of simplification. Then there was also this incident with self-driving cars. Again, this was a few years back, where they had this issue where there was this particular type of car. I don't want to mention the company, but particular type of car where which when it ran, so when it saw a red light, it would like slow down, but it wouldn't stop. Like it just kept on going. And so they sort of investigated into this. And one of the reasons for this was because the braking system that they had used in another type of car. And what it had learned is that when it sees a red light, because it's an automatic training system, right? So it's not like people had provided rules for it. So what it had learned essentially is that when the car sees a red light, there's something called as a lurch, which kicks in, and only when that kicks in, you actually stop the car. But when they transferred this into a different car model, that lurch never really showed up. So the car just basically just slowed down, but it wouldn't stop at all. So things like that, like debugging of systems, can also be is one of the sort of main applications that explainable AI could be used for. Then this is also useful for like identifying confounders. So again, this was a case where there was a data set where people found that having pneumonia was negatively correlated to you having diabetes. And I mean, I'm no medical expert, but even to me, it sounds kind of orthogonal, these two things. And it's actually the case that they are. It just so happened is that a lot of people with essentially pneumonia would go essentially to the hospital, and so you would get checked out for other things too. And most of these people didn't have diabetes. So, but if you train like a classifier, it would think that these things are negatively correlated, when actually it's just like there's actually a confounding effect because of which this happens. So these kinds of aspects also can be uncovered by doing explainability. And last but not the least, but in general, like to get optimal performance out of many systems, it's probably not sufficient just to have an automated system, because humans also have a lot of sort of independent or complementary knowledge that could be useful. So getting the best out of the system, you probably want something that's sort of human in the loop. And for this, obviously, you need a way to communicate with the machine. So to get sort of the best final performance. And then there were these cases which were also seen with sort of bias in images, as well as this on the right side is a very popular example where a classifier was trained to sort of distinguish between wolves and dogs. And again, it had very high accuracy. But when people actually tried to look into why this classifier was doing so well, it turned out that essentially most wolf pictures occur in snow. So what it was doing is basically if it saw snow, it would say wolf, otherwise dog. So it was basically just a fancy snow detector. But things like this, so which for that specific data set, obviously you'd still perform well. So you don't really care if you just cared about that set. But if you wanted to deploy this model, right, in general for say detecting wolves or dogs, you really wouldn't want to do that because it's not really relying on any salient features. So, I mean, all these aspects besides sort of test set accuracy, right, like are very important for widespread adoption, because you want the system to be sort of robust to many of these changes, as well as be sort of transparent in terms of what it's picking in what parts of the space. So now if we look at explainable AI, there are a lot of methods and stuff, but you can kind of partition them into these three categories as directly interpretable versus post hoc, global versus local, static versus dynamic or interactive. I mean, the last one is pretty obvious what it means. The other two, I'll sort of go in the next few slides describing what each of these things mean. So directly interpretable is basically the simplest thing, which is basically like models which themselves, lend to understanding. Like, for example, like decision trees, where you can actually just follow a path and see why a decision was made, or rule lists, which again give you very clear-cut sort of understanding of how decisions were made. So these kinds of models fall under sort of the directly interpretable category. For deep neural networks, of course, or like even complicated ensembles, which is many times the case in industry, like generally it's not just a single model, but it's usually a combination of models that are used. So for such kind of things which are not which do not directly lend themselves to understanding, you need sort of some post hoc mechanisms to understand them, that is after the fact mechanisms. And these are called as sort of post hoc techniques, which will sort of delve into these models and try to figure out what's really happening. So this falls under the post hoc. So one example of post hoc, which is arguably one of the most popular methods and also the simplest, although it has a bunch of issues, but is this locally interpretable model agnostic explanation method, or LIME. And what it does is the following. So if you look at this left figure, where you see this blue background, and then there is some like pinkish or brownish background. What the brownish thing is showing you is some decision boundary of some complex classifier in this space. And what you want to do is many times is not really globally understand this whole boundary, but like ask questions about specific parts or specific points that lie in this boundary. So for example, here, the bolded red plus sign that you see, it say would correspond to say a patient or something, and you're asking, why did I receive this treatment? So the plus sign would be a specific instance, and you want to understand why did the model make this decision for this specific instance. So what this method LIME does is basically it'll take your point and then sample maybe hundreds or thousands of points around your point of interest, and then fit like a sparse linear model on top of that, and say that whatever features come up from this model are the reasons why your complex model essentially predicted that. So it's trying to basically sparsely linearly approximate the decision boundary around that point. So it's a very simple thing, but that's one of the sort of first methods that was proposed for this post-op explanation kind of idea. And this is there, I mean, this method works for different modalities like, tabular, text, image, and so on. A counterpart of that in some sense in images where you actually have access to the model is this saliency maps, which also is basically kind of the same idea, which basically takes an image, and what it tries to do is it's kind of doing kind of a sensitivity thing where it's trying to see how much does the output change if I perturb the input a bit. So if pixels which you perturb a little bit produce more change to the output, then those probably are more important, and so those you should highlight. So what you see here is basically in the top row you have the actual images, and in the bottom row is sort of a heat map on what it thinks are the most important sort of pixels in each of these images. So for example, here in the leftmost, you can see like the board part is more or less highlighted. In the middle, some of the like stuff kept on the sink is highlighted, and on the right, the structure is highlighted. So you can come up with these kinds of sort of heat maps, which people use as explanations of what the model is trying to focus on. So that's in the post-hoc local category because you're explaining single models. Single instances. But there is also like a counterpart for the global category where you're trying to understand the whole model itself. And there are ways of, doing knowledge transfer methods essentially that are used here. So because you want your complex model, you have your complex model and now you want to understand it, but you want to use a model that you would understand. So you would use some simple model like decision trees, random forests, or maybe even a small network in some cases if you care about some other things. So, and these you want to approximate the behavior of the complex model and globally. And so for that, there are like these knowledge transfer approaches where, like, for example, knowledge distillation is one. And then we had proposed a few in the last couple of years for doing this kind of thing where you can essentially train these models in such a way using the predictions of the model you want to understand, the complex model, so that it replicates as best as possible its performance. So there are also methods in this category. And in general, though, like there's no single sort of explanation that may serve everyone. So there are different kinds of explanations. The ones that I showed you guys now were more like feature based, but you could also have exemplar based explanations. That is, say for example, if you were recommended a particular treatment, you might want to know which other people were also recommended the same treatment and how their results were, because that might give you some confidence in the treatment, because you may not understand, right? Like the actual medical aspects that might be important. So that might be actually uninterpretable to you as just a regular patient. But like I said, you can also have feature based. So which are some of the ones that I showed, right? Like where, say if your loan is denied by a bank, right? You might want to know why was your loan denied and so on and so forth. So these kinds of aspects, but those are essentially different forms of information that you're asking. So actually, if you look at what I've just said, right, like generally all the methods and most of the stuff that's there actually corresponds, in my view, to these two stages. So in stage one, you can think of essentially trying to uncover what's really truly happening in that model. And stage two is the communication part, because it's not enough to just uncover what's truly happening, because then you can, in the most trivial sense, just replicate the original model and give it to someone, right? Because that is truly faithful to what's happening, but nobody would be able to understand it. So, so you need the second aspect of sort of mapping to the mental model of the person trying to consume it as well. And then once you have that, there could be also a feedback loop where you try to, optimize this two-stage procedure. But this is what really most of the methods are trying to do, where they're trying to sort of uncover things as faithfully as possible to what's truly happening. And then in second stage, trying to as simply as possible convey these aspects to some consumer that's actually interested in understanding these explanations. And as you can see, like the first part is kind of more easy to formalize, because it's just, rather than having all this theory for data sets where you train a model, it's mostly just about a model and fitting another model and seeing how accurately that other model might replicate this model. So that's, in some sense, from like a computer science perspective, it's easier to formalize. The second part is obviously harder because it relates to mapping to a human's mental model, which I mean, we don't have really a very good handle on. So that part becomes more challenging in that sense. But you still need both these parts, because even like I said, as the second part is important in mapping and conveying, you also need the first part, because you could just otherwise just come up with lies, right? And I can communicate that very easily, but that's still useless. So you need both of these sort of aspects. And most of the current explainability methods, they do not sort of explicitly state this fact, and they are trying to do these two aspects simultaneously in some sense, without actually sort of expressing them. So for example, like the line method that I showed you, right? Like where it just tries to fit a line, linearly approximate your boundary. It basically trains a lasso, which is like a sparse linear model. So what it is trying to do is, because it's trying to fit, it is trying to do stage one by trying to fit as accurately as possible around the instance that you care about. But because it's sparse, it is the reason they have sparsity so that the person will understand, because so that you don't get like 100 features that it points to, but rather maybe like 5 features or something that are more consumable. So most of these methods, if you see, like try to go for like sparsity with fitting accuracy, because they're assuming that sparsity is basically a proxy for human understandability. So it's a combination. So they're trying to do these two stages of faithfulness and communication in the same sort of breath, so to speak. But given this sort of disentangled perspective, right, there's no reason that we have to do this in one stage at the same time. So the typical approach, like I said, is like the top of this, where you just have stage one and stage two, and you just try to learn some sparse model or something like that. But if you sort of decouple these two aspects, there's no reason that you have to go to stage one to stage two in just one shot. Like you could even create, for example, a sequence of proxies that where each of them in between may not be essentially understandable. But what happens is the final thing that is going to be consumed, it might actually have a better performance if you fit to these intermediate proxies than fitting directly to the original model. And this kind of makes sense, because that's anyway indirectly one of the motivations for many of these knowledge transfer approaches, where the way they build more accurate models is by building approximate models, and fitting to the approximate model turns out to be better just because it's related to sort of function smoothing. So it's because the layout of the decision boundary space is much more smoother, so some simpler things fit much better. And eventually the thing that you fit is more accurate with respect to even the original thing. So what I'm suggesting here is that so you can come up with a plethora of new approaches basically here, where you don't have to go really directly from faithful. You don't have to directly essentially put trying to get something faithful and understandable in the same breath, but rather splitting it up and getting it in sort of multi sort of step approaches. So and I'll show you just a quick some examples of what we have already tried with that. And like I said, there are many applications of this kind of like simple thing, model transfer. So one is domain experts preference. So for example, like I worked with engineers from the semiconductor industry for quite a few years. And for example, they trust decision trees a lot. So even if you give them the most accurate neural network, they won't care, because They want something that they can understand, because if something goes wrong, they can't just say that, oh, this model is accurate, that's why we sort of followed its decision. So if they care about decision trees, then what you want is to build the most accurate possible decision tree. And so this is where all these knowledge transfer things come in, or even small data settings. So like you might have like huge public corporas where you have trained something, but now when you go to a specific client data or this, they might have very small data sets. So how do you use something? You cannot train a huge network there because it just overfits. So what do you do there? Or even in resource constraint settings like your cell phones and things like that, you can't deploy like very huge models because of memory limits and power limits and so on and so forth. So then all these knowledge transfer things come into being. So these are some applications, like besides just explainability as to why you would want like to transfer knowledge to some of these smaller things. And here's a synthetic example of this idea that I was mentioning. And then I'll show you just a table with some actual real data. But this is just to make just to drive home the point. So what you see here is basically just some synthetic functions. So what you have here is this red curve that you see with some jaggedy stuff, like it goes here, is basically say assume that that's your true like black box model. And here in this case, it's some 5th degree polynomial, okay? And with some like 20% noise. So that's why there are some zigzag things. But the red line is what you really want to essentially fit as closely as possible. But your simple model, which may be just like we are using some like linear, maybe just a linear regressor, okay? So now, if you just directly fit to this 5th degree polynomial, you get essentially this yellow line, okay, which has basically some mean squared error of say 2.29 in this case. So you get, if you just directly fit, you get this thing. Now, however, like I was saying with this multi-stage thing, what you could do is you could fit, in this case, this blue curve, which is a 3rd degree polynomial to this 5th degree thing. And now to this 3rd degree, you fit a line. And what you get is this green line. And as it turns out, its mean squared error is less than half of directly fitting. So even though it's 2 stages of approximation rather than just direct approximation, this actually leads to better performance in this case. So you could even get better models by basically essentially doing this multi-stage approach. And the complexity of both these models is the same because they're just lines with the same number of features. So there is like some hope here in terms of doing this, and this generally happens like there's some details, and we have actually a paper on archive on it, but the point is that it can actually help, which is kind of interesting. And here is actually like some more like sort of more experimentation on some real data sets like C400 and then some other UCI and so on. So for data sets with different complex models like neural networks and boosted trees and so on and so forth, and then using simple models like just a single decision tree or some Linnet model, and then different transfer schemes, and then using one hop as opposed to like this multi-hop. And this multi-hop more or less does the best in almost many of the cases, almost all the cases. So yeah. So
Amit, maybe the previous slide, the one previously, this one, just as an intuition, why is the intermediate 3rd degree polynomial is giving us a better intermediate to a better fit than using the original 5 degrees samples?
So it's interesting. So I didn't know how deep to go into this, but so
go ahead. Let's try.
So that's a great question. So the reason is so at a one level higher, it's because it's all about function smoothing. So you have this noisy signal, right, which is there, which you're fitting based on whatever its loss is. So in this case, I think it's bi-squared loss or something like that. So you fit this, and now once you fit a lower degree polynomial, firstly, it is kind of smoothing out the noise. And what happens is that since the loss that you're minimizing for these models is different than the evaluation loss, which is anyway many times the case, even for standard neural networks, right? Like you might train using cross entropy, but that's not how you're evaluating. Like a human will probably evaluate it based on 0-1 accuracy, 0-1 loss. And that's what's generally used, right? Like if it's correct or not correct, kind of. So whenever there are these loss mismatches plus some noise, like intermediate sort of the function smoothness like matters a lot, because what's happening here is I think essentially the noise aspect is kind of also nullified by this intermediate model, which is trying to approximate this boundary. Plus, there is this loss mismatch thing where although these guys are trying to minimize whatever some, in this case, bi-squared loss, since the final evaluation is MSE, it does not mean that directly fitting something to the original will give you the best results. So
And
these
if
are
you
some
would
of,
have,
yeah, go ahead.
if you would have used a fifth degree polynomial as an intermediate, I'd assume the results would be even better, no?
No, so it depends, because it also depends on the gap of whatever your final thing you are going to evaluate, right? So here what I want to do is basically build the best linear model that I want in this simple case, right? So like I was saying, it also matters. So now this linear model, if I fit to something very complicated, even though it is very close to the original thing, because of this gap, it may not still be able to do well. So there is some, but the third degree one is much simpler than the fifth degree one. So fitting to that is much easier for this guy. So there is some trade-off in terms of faithfulness to the original thing that you're trying to replicate, but also how complicated is that thing that you're trying to replicate. So if you lower the bar, but don't lose too much, then it's better to fit in some sense to that thing. And that's kind of one of the intuitions here. So which is kind of very interesting, because you wouldn't expect that, right? Like you would expect that give me the most accurate thing and I just fit that and that's that. Like why would I need anything else in between, sort of? But this shows that actually having in a way it's like a teacher thing, right? Like, I mean, you might have like a genius in some area, right? Like he knows everything, but he may not be a good teacher even though he has the most accurate information. And many times teachers are like may not be like the best people in that field, but they're just really good in communicating and simplifying things. So it's some sort of, if that's more sort of a indirect philosophical thing, but that's kind of the intuition too here, that the best teacher may not necessarily be the best model, like the most faithful model. You just want something that's good enough, but is also able to sort of communicate somewhat better to the thing that you finally want. So there's this interesting sort of trade-off, which we sort of in real life we say sort of all this abstractly, but I think it's nice to see this actually mathematically, in the sense that you do this and this actually happens. So you can even try this out, I mean, using Python or whatever. There's some details, but yeah, like it's just some fifth degree and I've added I think 20% noise and stuff, something like that. It's a very simple setting, but it happens even in this setting, which is kind of interesting. I mean, this is one of the first things I tried because I wanted to see if it actually made sense or not. So I just wanted something very simple just to see like, oh, what happens, and it actually worked. So.
Cool, thank you.
Yeah, and so this is the archive link there is like for that paper, which has like this information in case anyone's interested. So
by the way, before I forget, I don't think we have the lecture slides. I don't know if you told me if you can send them. Huh?
I'll email them to you.
And I'll add them to the recording so everybody will have.
Okay, sounds good. And okay, so that was that. So are there any more questions on that? Or... Okay. So now there's also a lot of talk about causality and stuff these days. And people are trying to sort of sell, like saying, oh, I think not correlation, causation and stuff. So one thing I'll point out, I mean, we can have a broader discussion on this if time permits, I guess. But just having something causal sort of replicate does not mean that you still have an understandable model. And this is what this slide shows, that even if you have the most accurate causal model, it basically still corresponds to just stage one, because firstly, the graph can be huge to consume. Secondly, the graph can be based on some hidden or latent variables, which may not themselves anyway be interpretable. So so just because you have sort of a causal generative process does not mean that you would have something explainable. So that's one point I wanted to make. The second thing is that this is kind of interesting. So a few years back, Jeff Hinton had said that, do we really need explainability? And we don't really need it. Might actually slow down things and so on and so forth. So it's kind of an interesting article, which you can look at. But from my perspective, I mean, yeah, like actually I was also kind of, even though I'd started, generally, I was still critical, like, do we really need it? But I think the more and more I've sort of worked in it, I felt like there is actually more and more reason to have it. I mean, besides those sort of obvious things that are told to people in terms of why it's needed. So, but nonetheless, I think this is a pretty interesting article to look at. And one of the main criticisms, right, for explainability is like, how can you understand like you have a huge neural network, there's so many neurons and stuff like that. How can you even begin to imagine to try to understand this thing? I mean, like you're just making up some stuff, basically. That's the general perception. But my general sort of argument is that, so like people trust people, right? And it's not that I know which neurons are spiking in your brain or which connections are being activated and so on and so forth. It's through emergent behavior in the real world. So my point is that you don't have to, just because if someone says, oh, how you have some explanations for this, but how do you know like this neuron is doing this or that, or those sets of neurons are doing that? My point is that you don't have to really understand something or understand a network, or you don't really have to understand every neuron activation or every layer activation. What you need is just one faithful representation of that. And that's sufficient to say that you understand the thing. And this is very similar to humans, right? Like you can think of human behavior as basically an embedding or a representation of the neuronal activity that's going in your brain. So based on this representation, which I do understand, which is your behavior in this world, I will make judgments about you and decide how I want to interact with you. And that's sufficient. I don't need to know like which neuron was firing at which point. So as long as, I mean, this representation may not be easy to obtain, like we have seen also in the real world, trusting people may not be that easy. But the point is that one faithful representation is sufficient. If you do obtain it and are able to understand it, it's sufficient to claim that you understand that system or model, which is, I think, reasonably interesting claim, because that means that if someone comes up to you and says, oh, but you don't understand this, how does this part work or that part work, based on some other representation, like in this case, neurons or this, you don't really have to be able to understand it to claim that you understand. So, so I think this is a point I think that I wanted to make. Okay, so this is more of the stuff that I wanted to say in terms of ideas. Now, what I was going to do is just sort of quickly take you guys over like the toolkit that we released a few years back in 2019. But yeah, I don't know before that if there are any questions from Alejandra or anyone. Okay.
I would say a comment. Go ahead. No, go ahead.
No, my only doubt is, I'm a neuroscientist, so obviously I understand when you say we don't need to understand what each neuron does. But if we don't understand, in a sense, how is it any different than normal neural networks? Not understanding what they do, how is that different from explainable AI?
Yeah, so in this, yeah. I mean, no. So like from a systems standpoint, like I understand from neuroscience, because I have also worked with a bunch of neuroscientists and stuff. I think it's good to obviously understand the system from the core. But what I'm claiming is, if you have a system, right, like it's more like the neurons and stuff are like sort of in some sense, I mean, I don't mean to like belittle it, but is an implementation detail of that system, right? But say if I have to understand that system, there are various levels at which I can understand. If I want to, it depends what I want to do with it, right? So if I want to create another brain, then I probably have to understand like how the neurons work or how interconnections happen and stuff like that. But if my point is just if I should trust this system, what my claim is that from that point of view, what is sufficient is basically seeing a manifestation of that machine in some representation that you understand. And as long as you're able to replicate the behavior and validate it in that space, that is sufficient for you to be able to say that I understand the system enough to sort of trust its decisions, rather than having to understand each and every firing or like thing at that level. That's basically my claim.
Yeah, it makes sense. We also understand how neurons work or their activation. That makes sense. Thank you.
Yeah. Okay, so this is a toolkit that we released a few years back called AI Explainability 360. And there are also a few others that we actually have released, like there's the adversarial robustness and AI fairness and so on and so forth. So this toolkit actually in the last 2 years has also been taken by the Linux Foundation. That's because they found it to be quite useful. So now it's been donated there, and they've been it's under them now. But nonetheless, it's still, I mean, open source, and anybody can add stuff or edit, and there's been a lot of stuff going on. And like I said, there are many explainability methods, and before I essentially showed you guys like split into 3 dimensions, but this is a little more granular split that we developed in terms of like a taxonomy of what things are generally there. Although the leaves of this tree are basically the methods that are there in our toolkit, AI X360. Essentially the categorization is pretty generic. I mean, it's based on generally looking at the whole explainable AI kind of area. So let me just briefly take you through this tree. So the root is basically either you can have static or interactive explanations, and there's a lot of work on static. So in that you can either explain data or you can explain models. Again, there's a lot of stuff on models mostly, but you can also have explanations for data. And in that, if you want to understand a data set, it could be, like capturing few representative samples of the data set as a illustration of what's happening in the data set. Or it could be also like learning high level features. So which happens a lot with, especially with the computer vision, right? Images like pixels are not really interpretable. So you want to do some kind of disentanglement and come up with higher level features. Like if it's face images, maybe like pose of the face, or like so certain properties that are more sort of understandable in terms of human language. So you can have explanations for data, then you can have explanation on the model side. Again, you can have local or global, which I've already talked about. So local is instance specific explanations, and global is globally trying to understand the model. And then in local, you can have post hoc. I didn't talk about self-explaining because that's not, I mean, it's there, but it's not like one of the more popular ways. Post hoc is quite popular. But self-explaining is basically where your model is not directly interpretable, like a decision tree where you know globally what's happening. But nonetheless, it is able to give you explanations for individual instances. So you cannot interpret the whole model, but it itself gives you explanations for why, for example, it classified this cow as a cow. For example, it might show you some pixels. So you don't have to apply some additional algorithm on top to figure this out. So those are kind of self-explaining methods. Yeah, so you can have that. In post hoc, again, you can have like explanations based on samples or explanations based on features. And in the features, like I had Lime, like I had mentioned, but there are also SHAP, and there are also some things called as contrastive or counterfactual explanations. So which basically help you with like, what if you change this, what would happen, and so on. So those kinds of methods also fall in this category. Under global, again, you can have direct, which is like I had shown you, like the trees or rule-based methods, or you can have, again, post hoc, where you have these sort of knowledge transfer schemes from things. So these are essentially the types of the categories, and essentially the leaves are the methods that we have. So I'll show you quickly, like I'll take you to the website, and then I'll also take you through maybe a demo just to show you, like, just to give you a flavor for what these explanation methods are like, and then maybe even show you a notebook with those methods. And these are like some of the classes like that are there. You don't have to go too much into detail, but essentially if people wanted to contribute, yeah, you can add to one of these classes. Okay, so
by the way, which classes need more contributors? Can you point out for somebody maybe watching that wants to get into it?
Yeah, sure. I think all of them, we would welcome contributions for all of them. So like I said, you have directly interpretable unsupervised, which is like for data. There is directly interpretable supervised, which is like the Lime kind of stuff. We have decent amount there. Then you have local black box explainer, local white box explainer, global black box, and global white box. So we would welcome contributions for any of these. It's not, no need to prioritize. Okay, so now let me go to this. can you see my the web page? Or okay, cool. So this is the web page. So it's AIX360, my Blueberry start. I mean, on Google, if you just search for AIX360 or AI Explainability, it should come up. So besides, if you do get code, it will go to the GitHub where all the code is for all of this. And it has pretty standard instructions of how to install and so on and so forth. But we also have created this website with a lot more information. So for educational purposes also, so that people can read about and get more familiar with this whole space. So we have like resources under, so there's an overview of this thing, this space, and like other toolkits, and then some guidance, like the tree I showed you. So the similar kind of tree is there, and then with like a bunch of like explanations for different things and different categories for what they mean. And then glossary of common terms used in this space. Also papers that have led to this toolkit. And then tutorial notebooks. So these, I'll actually take you through one of them quickly so that everyone can have an idea. But these are basically Jupyter notebooks that you can, once you install a toolkit, will be available to you and you can play along with them for different kinds of use cases. So one thing, let me show you is, okay, so if you go to the home, if you go, also there's a Slack community in case people want to join and have questions. So there's one quick demo I can show you just to get an idea. So this is, this was a challenge run by FICO a few years back called the FICO Explainability Challenge. And the goal was like they gave a data set with different kinds of risk factors and different kind of things for HELOC loans, that is home equity line of credit. So what they had is basically different individuals, different facets, sort of like their financial health, showing their financial health, and if a loan to them was approved or denied. And that was essentially the data set. And essentially they ran a challenge where you had to train some sort of models and explain why certain people were, for example, denied a loan and why certain people were approved a loan. So this data set is something that's publicly available it's easy to get it. So it's publicly available, but you have to send, I think, the FICO folks some emails so as to download it or something like that. So this is what they did. And so actually our team won this challenge, which was a few years back. And one of those algorithms is also part of the toolkit. So, but let me show you like what kind of things the toolkit can sort of offer. So for example, like I said, like different folks might need different kinds of explanations. And so we created essentially here 3 personas, like a data scientist, a loan officer, and a bank customer. Of course, I mean, you might want different kinds of explanation, but this is just like a general thing that we thought would be sort of appropriate. So if you're a data scientist, for example, so if you click on data scientist, then you go next, he might be interested in the overall logic of what's happening. So what is the model doing and what is it actually doing at a global scale? So here, for an explanation, you might want to use a directly interpretable model, because I want to understand, like before deployment and generally, what are the factors this model is relying on. And so if you train a directly interpretable model, so like in this case, like a rule-based model, so I won't go too much into detail about the training, but what it will do is it'll give you these kinds of outputs. So it'll have some accuracy, but it'll say that, for example, like this external risk estimate. So this is like a credit score, for example. So it is saying that for every increase of 10 in this external risk estimate, increase the score by this. So what is this score? This score is basically, so the higher this is like a credit score. So a higher increase the score, which is basically like the probability of you getting a loan. So it's saying that if for every increase of 10, what this model is saying is that your chance of getting a loan will increase by this much. And you can see, like, you can get plots of this form to understand like how this factor, external risk estimate, actually affects your chances of getting a loan. And then similarly for some of the other things. So there's some net fraction revolving burden and so on and so forth. These are all like financial indicators essentially, and months since most recent delinquency and things like that. So, and how they would affect essentially your chances of getting a loan. And then, so what you could do is you could do some sanity checks essentially before deploying. If these factors should be the ones that you should rely on, and secondly, is that the trend you would want, more or less. So you can do some sanity checks with this kind of model. The second may be like a loan officer who say has decided, who has to decide basically if to approve someone's loan or deny someone's loan. And so he might decide, say, to approve someone's loan, say he has decided to approve Alice's loan. He might want more sort of confidence in that decision, seeing that are there similar people whose loans were approved by previously and who sort of repaid them. And this method called essentially protodash does this. So Alice was the person that you wanted justification for, but it found, like, for example, 3 other people like Mia, Kate, and Carla, who it is saying that, okay, these people are also similar to the person that you looked at, and all these people's loans were approved, so it's probably okay. And these are the factors that are common to these guys, or very close to the applicant that you want to approve. So you can get diverse and representative examples like that. And then if you're a bank customer who actually submitted the application, what you would care is, if your loan is approved, you would mostly not care, because generally you would care for a negative decision. That is, if it was denied, you would want to know maybe why it was denied and what could you change so that it's approved maybe the next time you file it. So this kind of explanation method called contrastive explanation method, what it does exactly that. So what it says is, even though your loan was disapproved right now, these 3 factors which are there, if they change from this to this, your loan actually would have been approved by the system. So the next time you probably try to apply for a loan, you can maybe try to enhance some of these factors if they're actionable. So for different folks, it will give you like these kinds of criteria, that not only why something happened for you, but how you could change your essentially status. So these are the kinds of insights you could get. Essentially there is, yeah. So, and there are also a bunch of other methods, but this is kind of like just to give you a flavor of the diversity of things there. And so there's also, like, if you go to tutorials here, you can also go here to the GitHub, but it will essentially open a notebook, which also you can run. So we don't supply data sets, so you will have to actually download those data sets from, like, we provide links where to find them because of legal things. So you just download it, put it in the specified directory, and it should run. But this is exactly for this FICO data set that I was saying. So you have this FICO data set, and these are the different features in that data set. Like I said, external risk estimate, months in sold age trade, and so on and so forth. There are a bunch of these things. And like I said, the thing is to predict, what is the likelihood of your loan being approved, essentially. And then you have this these methods, these rule-based methods there. So BRCG and log RR are 2 rule-based methods. So for that, you first, load and process your data. And this is an example, sort of just a few, data samples for each of these. So there are 5 data samples here, just printed. And then these rule-based methods require some binarization of the data. So the real attributes are binarized, so it shows you here what it does for binarization. And then the BRCG rule-based system. So the first rule-based system you run, it actually gives you a very simple rule here. And it has a, I think, accuracy of almost 70%, 69.7. And what it's saying is basically this is the rule. So it's saying that if this external risk estimate is less than 75 and number of satisfactory trades is less than 17, or if this external risk estimate is less than 72 and number of satisfactory trades is greater than 17, then basically deny the loan, else you can accept the loan. So this is, even this simple one rule based on all these factors can give you around like 70% accuracy in terms of predicting goodness. And it's pretty interpretable because it's just a few factors. You can build more accurate models by, building more accurate rules. So this log RR, for example, will build a more deeper model. Like, so this is the model, like with the rules. So it's saying that, if this factor is greater than this, then add this much, and so on and so forth, and add this much to the probabilities or score, and so on and so forth. So this is hard to interpret directly because there's so many numbers and things can get repeated. But the way you interpret this is through these plots, which I showed. Like, so it'll give you plots of this. So this external risk estimate, it can show you how that affects output. in this fashion. And you can get like plots for each of the features that it considers important. So you can get which things are sort of negatively correlated, positively correlated, and so on and so forth. Yeah, so this is for the directly interpretable part. For the loan officer part, where he just wanted similar examples. So like I said, you have this proto-dash method, which will, again, you basically load the data set, you use the standard stuff, you show a few examples. Then this is some histogram of, for that for that feature, external risk estimate and number of satisfactory trades, how the data looks like. This is just for sort of getting a feel for the data. And then once you have processed and normalized, you train here. Since here, this is not a directly interpretable method. So you train some neural network classifier. And once you have trained the classifier in this case has a higher accuracy than the BRCG. So it has 72% accuracy, so a little higher. And now you want, like, for specific individuals, what were the other similar individuals? So in this case, we have said like the ID of the person is 8. And the prediction of the model is good. So now you want to see essentially, are there other people who are very similar to this person, but whose also loan was essentially approved? And this is the output it will give. Basically, in this case, it gives like 5 other people who have very similar. So for all of whom the output is good. So like essentially that means the loan was approved, but these are very similar to your profile person that you're interested in. And these are just some details on how feature similarities and all are computed. But the point is that you would get an explanation saying that, okay, there are other people where, sometimes 12 out of those 23 features are exactly same and others are close who have had loan approval. So maybe it's safe for you to also approve, or maybe it's not safe. So either way, you can make a decision based on this. And same thing you can do for someone whose loan is denied. You can do the same thing. And yeah, so that's that. And the third one is this.
How many people worked on this thing?
So you mean for the whole toolkit, or?
Let's say just on this HELOC example and everything behind the example. I don't think it's the whole toolkit, right?
Yeah, so just for this one, it's not much. I mean, the algorithm, so the proto-dash and CEM, I was one of the main people who developed those algorithms. So so we did that, but then yeah, but to create this notebook, so the first one, the BRCG, there was another colleague of mine called Dennis who developed that. So he did a lot of work on that. And then we had the lead software architect for this was Vijay. So it was basically mostly like 3 or 4 of us just for this notebook. But in general,
wow, just for the notebook, yeah.
Yeah, but to create this whole user and like this whole web page and all, yeah, we needed like, that was a big thing. That's why the paper has like around 20 people on it. Probably maybe, yeah, like maybe 10 of them were 15 were closely involved in the whole thing.
And what's in it for IBM to create all of this, have 20 people working on it?
Yeah, so I mean, we just started, it was just out of interest, actually. We just built it. It was, but then since this is an upcoming area to like, I guess IBM wanted to generate interest in this space. And now, because what's happened is like, if you can see, right, like the toolkit, so this was released 3 years back with 8 algorithms. And that time it was like really diverse and like a lot of things, no other toolkit existed. But now if you see, we have, I mean, not many have been added yet because IBM now is trying to sell the other part. So that's what it is in it for them right now, because this is more, now they're using this like a leverage point for, because a lot of people have used it. So a lot of clients we haven't even had to approach. They've just used it. So they've come to us, and now we have a bunch, like 15 more internal algorithms, which are not open, so which are going into product. So but that was, I think, not the initial thing. The initial thing was just to sort of see more exploration, just to see what the space is and stuff. Cool. But now it just turned into like, yeah, also like a business thing for them. So yeah. But this was, yeah, it was just mostly interest. Like we were just interested, so we built it. And we thought like it'll probably have a lot of interest. So yeah, so the CM method is one of the things which is contrastive, which, as I was saying, like a person whose loan is denied, he would want to know like how can he change his status? So this was something, I mean, I had thought of actually just through common sense, because there were a lot of explainability methods which are showing what is important. But I was thinking that, like, as humans, right, like when we think, when we describe, it's not just like we just describe what are the most important aspects of something, but we also say, oh, this person is different than this person because of this, and so on and so forth. So so like minimal changes that actually are informative in describing some other behavior are very much like captured by us when we describe anything. So I wanted to develop basically a method that captured that. So this was one of the, arguably like the first contrastive explanation method for like deep networks that we built. And now there are a lot of stuff on it, but this was like 2018, so 4 years back. Yeah, so this is just running. I mean, I won't go into too much detail, but this is the kind of output it'll generate basically. So say your original person was this first column, and what it'll generate is this second column essentially, where what it's saying is if this external risk estimate went from 65 to 80, this average months on file went from 52 to 65, number of satisfactory trades went from 17 to 21, then your classifier will actually change its recommendation from not giving you the loan to giving you the loan. So so it's not just about whatever important features are there for that specific decision, but how can you change the decision by minimally changing certain inputs. And this is the kind of explanation this will be. So this can you help you like give a feel for like, how the classifier is behaving.
How do you define minimal change? Like changing by 1 point, one measure is not equal to changing on 1 point another measure, right?
Yeah.
Or
So
does
here,
the user
I mean,
need to preset?
Yeah, so here we assume like a specific like elastic norm. So we say that, like the distance of the features as well. So it's like a L1, L2 thing. So it's number of features as well as how much you change each feature. So the distance function can be, like you're saying, you're right. Like for different things, the distance function may be different. In this implementation, it is that, which is L1, L2. But for if you know what is the distance function for your application, you can, in general, the idea is pretty generic. So it's given your distance function, you just put it, I mean, you would basically want to put in to this kind of general framework and do it. The code and all is specific for this elastic norm, this where you can change the, like there are like some hyperparameters and all which you can play with. But but that's the output it'll give. But yeah, in general, yes, if you know the distance function, that's what you should use. But the current thing changes. It does some balance between the number of features and the value amount you want to change each way. But all these are like it's not that hard to modify the code, where you can also say that it's just changing across all features, but maybe like for this credit loan, right? Like if you're submitting a loan, if this thing tells you, okay, reduce your age by 5 years, then you would have been approved the loan. It's kind of useless, right? So you want kind of features that are also actionable in some sense that you want a recommendation for. So, but you can, I mean, there are like not that difficult changes in the code that you would have to do something like that. Where you can fix certain features and stuff like that. And then it also gives you like this PN, which we call as pertinent negative. So this term, I actually, when I wrote the paper, I was searching like what term to use, and this is used in the medical domain. It seems quite a lot. Like for example, if you go for your physical, right? Like doctors don't just write normal. Like they will write like each and every aspect and what was the state. So they'll say like whatever like heartbeat was within this and this. And the reason is that the next time you do it, right? Firstly, for their own records, they know what all was checked. But also, if you change doctors and all, they know like what all was checked, rather than just saying just normal. So these pertinent negatives is like a term used in the medical field. But it's also like even in the sort of crime field, it's like relevant. Like for example, like if there is a crime somewhere and you find that. Like nothing was stolen, for example. The fact that nothing was stolen is probably an indicator that, like it was not just for theft or something like that. It was probably for some personal reasons that the crime was committed and things like that. So things that are not just present, but things that are absent are equally important in figuring out what's happening. And that's basically the point. And yeah, so then this shows that PN features as well as also, but it can also show you like which were the important features in the existing input. And those features also can be highlighted with this method. So yeah, so I think that was a lot probably. And there are a bunch of these notebooks. So I mean, feel free to play around. I mean, I just showed you guys one, but yeah, there are many other things. So yeah.
It's a lot of work. Very, very elaborate, Amit. Thank you for demonstrating it to us. I think the intro part for me was the most interesting to see the different reasons why we want explainability and what is explainability. It really depends on what's the end goal of what you want to explain and why. So thank you for that. Alejandra, yeah, I think this is our time now for questions. Otherwise, we'll wrap it up. If you have anything, it's a good time to ask now.
I think it was really, really clear, everything. I'm really curious to see the notebooks, actually.
Yeah, we'll also add the lecture slides to the recording once it's out. I'll publish it for everybody to see. Amit, thanks a lot for the talk today. I'm happy we got to do this.
Yeah,
luckily, really. I'll send you all the details once it's posted. We'll email. Sure. And I'll wish everybody who's going to see this recording, have a good day, good evening, good morning, wherever you are. And Amit, thank you again. Alejandra, thank you for joining. And we'll say bye for now.
Yeah, thanks for having me and thanks for joining. And good luck with your next ventures.